Hi, in this video, I will solve a problem from TIFR 2019 on quantum mechanics. So, I will first read the question. So, it states that the it gives the wave function of an electron in a hydrogen atom, and this is the form of the wave function. So, this wave function is basically superposition of different uh, states of electron in the hydrogen atom, and we need to find the expectation value of Lz and L square for this given wave function. That's the question. So first, before solving this, before getting the expectation value L square Lz, the very important step to check whether our given wave function is normalized or not. So what normalization means? Here the normalization means that the sum of the total probabilities whether 1 or not. So that we need to check. So here I will write the wave function again for your convenience. So this is psi of x 1 by root 10 into 1 0 0. It is 2 by root 2 by 5 2 1 0. It is 2 1 1 x, and final one is 1 by root 10 2 1 minus 1 x. So this is the wave function, and here each this 1 0 0 means 1 means n, 0 means l, so it is n l m. So which is the psi n l m is actually the eigenstate of an electron in this hydrogen atom. So we need to check whether this wave function is normalized or not. For that we need to check whether this total probability P total I am writing, whether it is 1 or not. It's just a sum of all square of all those numbers. So first one is 1 by 10 plus second one is 2 by 5 plus third one is also 2 by 5 plus fourth one is 1 by 10. So if I do it, it will, I guess, come out as 1 exactly. So it's normalized, no issue. Next thing, we need to know that what happens if Lz, the operator, acts on the hydrogen atom state psi NLM. What it gives? It gives this is the eigenvalue and this is the eigenstate. So this state is actually the eigenstate of this Lz. Similarly for L square also, it is also the so these two steps are clear. So these are these two operators are actually so this psi NL state, this state is actually the eigenstate of this operator L square as well as this operator Lz, which is very good news. Now we need to find this expectation value. Another thing I will use here, that expectation value of any operator is actually, we can write it as a sum of probability plus sum probability into the eigenvalue. What it means, suppose if I have a wave function, so suppose for this wave function I can think it as a, if I do this for Lz, I will write it. So if I do it for Lz, what it means, that as you can see, this state is a superposition of all those hydrogen atom states, and each state is an eigen state of this Lz operator. So if I want to use this relation, then so Pi is the probability of each state and lambda is the eigenvalue corresponding to each state. So now if I find the expectation value, what I will do, I will write the probability multiplied by the eigenvalue corresponding to the state. So what is the first? First is this one, What is the probability of this? This is 1 by 10. And what is the eigenvalue? This is m is equal to 0. So 0 h cut plus, let's go to the second one. 2 by 5 into, this m is also 0, so 0 h cut, plus third one, this is also 2 by 5, here m is 1, so into, 1 h cut, plus last one is 1, last one is minus 1, so 1 by 10 into, what is the eigenvalue? Minus 1 h cut. So this is very simple. I will explain it again. So here what I have done, so I know this expectation value is sum of summation over probability multiplied by the eigenvalues. So I apply this for this LZ. So expectation value of LZ is equal to, so sum over, so I break this sum into 4 parts. Sum over pi into lambda I. So since my wave function is this one, so what is the pi? So let's go to the first one. Pi for this one is 1 by 10 and lambda I is 0 h cut. For the second one, this is the second one. For the second one, pi is how much? 2 by 5, lambda I is 0. For the third one, similarly 2 by 5, but here lambda I is, what is the eigenvalue? Since the value of m is 1, so eigenvalue is m h cut, so 1 h cut. Similarly for the third one, 1 by 10 into minus 1 into h cut. So this is so this is the expectation value of LZ. Now similarly we will find the expectation value of L square. So what is the expectation value? We use the same rule, this sum of pi lambda I. So if I use the sum of pi lambda I, what is the pi for the first one? Same, 1 by 10. What is lambda I? L is 0. So 0 into 1 plus 0 is still 0, 0 h cut square. Second one is 2, 1, 0. L is 1. If L is 1, then pi is 2 by 5. If L is 1, then 1 into 1 plus 1 for this also L is 1. So 2 by 5, 1 into 1 plus 1. And for this 1 by 10, for this also L is 1, so 1 into 1 plus 1. So basically this is 2h cross square, 2h cross square, 2h cross square. So yeah, I can take that 2h cross square common, then 2 by 5 plus 2 by 5 plus 1 by 10. 2h cross square, 4 by 5 plus 1 by 10. So I can take 10 common, then 8 plus 1 9, 9 into 2 18, and then 9 by 5 cross square. So is the solution. So I'll go through this problem again for clarification. So the problem states that if this is the wave function for an electron in a hydrogen atom, which is basically superposition of different states of the hydrogen atom, different states of the electron in the hydrogen atom. So you can see 1 0 0 is the ground state, then the first excited state. So it's a superposition of all these things. We need to find Lz and L square expectation value. So I just wrote this wave function again, just for your convenience. Second step, I check whether the wave function is normalized or not. If it is not normalized, then we need to normalize it. So for normalization, what it means, we need to check whether the sum of total probability is 1 or not. So P total, I got what is this? 1 by 10 probability plus 2 by 5, 2 by 5 plus 1 by 10, which turns out to be 1. Fantastic. We don't need to worry anything now. Second thing what I did, I just wrote it what happens if LZ operator at some this state of an electron in a hydrogen atom. This is the generic one. This it gives me mh as the eigenvalue, and this is the same eigenstate. Similarly for this one, L square, the same thing. Then I use this relation expectation value of any operator for any given wave function. So if this reference, this you can see, so I am writing the reference in the Griffith's book, Quantum Mechanics, chapter 3, if you have doubt. So this is, I am just using a simple relation. You don't need to then take the all average or putting this from that side. So this, what it means, expectation value of an operator is just the probability multiplied by the eigenfunction. So if I look the Lz in that using this formula, so what is the probability of this state? 1 by 10, and what is the eigenvalue? 0 h bar. So similarly I did it for all of them and just I did the sum. Fine. So this gives me the Lz, and similarly I do it for L square also. So just if you have any doubt, just check this in the Griffith's book, or if you have still any confusion, you can write your comment on this video, so we can discuss there. Okay. So thanks for your attention. Next time we will come up with some other problem. So if you like this video, please share. Thank you.